Today we will start with sister algebras. So, we have seen properties of Banach algebras and we saw multiplicative linear functionals and the space of multiplicative linear functionals. They were in one correspondence with the maximal ideals, and that was a topological space sitting inside the unit ball of the dual of the Banach algebra, right. So, we got a compact Hausdorff space and then we defined what is known as the Gelfand transform. Now, we will define what a sister algebra is and we will see that the Gelfand transform is actually an isometric isomorphism for a sister algebra. Thus, identifying the sister algebra, the abstract sister algebra as a space of continuous functions on a compact Hausdorff space. Okay. So, that is the culmination of all this called the Gelfand-Naimark theorem. Okay. So, let us start with the definition. Okay. Right. So, we start with the definition. So, a Banach algebra. So, this is a Banach star algebra. So, remember star is a involution on A, right, order 2 and so on, is called a C star algebra, is called a C star algebra if x star x. So, x star makes sense because we have an involution. The norm of x star x equal to norm x square. Okay. So, the definition is very simple. So, this immediately implies, so it is already a Banach star algebra and you have this extra information on the norm, that norm of x star x equal to norm x square, right. So, this immediately implies, so hence norm of x star will be equal to norm of x, right. So, in a sister algebra this is going to happen. Why is that? Because you start with norm x star x, right. So, this is equal to norm x square, okay. Of course, less than or equal to, because I have a product of two things x star and x. Banach algebra property will tell me that this is less than or equal to x star times norm x, right. So, one of them gets cancelled and we will get norm x is less than or equal to norm x star, right, and by symmetry you will have the other one as well, right. So, we will also have that x norm x star is less than or equal to norm x in a similar manner, right. So, that is why the norms are same. Okay. So, sister algebra is quite nice and the examples you can keep in mind are two typical ones. One is I take a compact Hausdorff space and look at C of x, right. C of x we know is a Banach algebra with respect to the supremum norm, right. And what is the star operation? So, if I take f in C of x, the star, the involution is f star at x equal to f x bar, right, the complex conjugate, that is the usual star there, and then you see that it satisfies the sister algebra identity, right. What is the sister algebra identity? F into f star. So, that is mod f square, L infinity norm of, that is the supremum norm of mod f square is same as the supremum norm of f and you take the square, right. That is precisely what the sister algebra identity is. 1, 2, H is a Hilbert space, Okay. So, the first example C of x is very nice, this is commutative and with identity, right. So, constant function 1 is the identity there. The next one is going to be non-commutative. So, you take a Hilbert space and look at B of h. So, B of h is bounded operators on h, right, and there is a natural join there, right, t going to t star, right. So, t going to t star is the involution, right, and then from function analysis you know that norm of t star t is equal to norm t square, right. Why is that? T star t is actually positive. So, you look at t star t x inner product with x, right, that is a self adjoint operator. So, if I take supremum of modulus of this, I will get the norm, right. So, this is norm T x square and then I take the supremum supremum over the unit ball, I will get norm of t star t on the left hand side, norm t square on the right hand side, right. So, that is precisely the C star identity. So, these two are typical examples, and essentially these two are the examples or closed subalgebras of BH, right. These are the examples you can think of. Okay. Anyway, we will come to these examples again and again. Okay. So, let us start with a result on C star algebras. So, proposition. So, we are going to study Gelfand transform on these C star algebras, and we will see that Gelfand transform is actually a very nice map. Okay. So, first thing is, if A is a C star algebra, then A is symmetric, then A is symmetric. So, remember symmetric Banach algebras, that means this if you have the star operation under the Gelfand map, it should go to complex conjugation, right. So, symmetric means, so A is symmetric means I take x star and I look at the Gelfand transform, that should be the Gelfand transform and then take the complex conjugate. So, the star operation goes to the star operation on continuous functions on the other side, right. So, any C star algebra is a symmetric symmetric Banach algebra. Okay. So, proof. Well, this okay. So, maybe I should have said that this is also equivalent to saying that if x star, because this is what we will prove, x star equal to x implies x hat is real valued, right. That is the definition of symmetric Banach algebras. Okay. So, let x equal to x star. So, that is a self adjoint element in A, and you look at the Gelfand transform and you want to say it is real valued, right. So, you take phi in the spectrum of A. So, remember the spectrum of A, that is the collection of all multiplicative linear functionals on A. Okay. Suppose x hat of phi. So, we want to say that x hat is real valued, right, that is the aim to prove that A is symmetric, that is what we need. So, let us write it as alpha plus I beta, where alpha is a real number and beta is also a real number, right. So, we want to say beta is 0, right, that is our aim. Okay. So, for t in the real line, consider these elements in my in the C star algebra A. Okay. So, consider x plus I times t e. Okay. So, these are elements in A, right. X is an element in A which is self adjoint, I times t is a complex number, E is an element in A. So, this is an element in A. Okay. So, let us call that Z, so that it is easy to write down. Then thus phi of Z. So, remember phi is from the spectrum of A, it is a multiplicative linear functional. So, it is phi of x plus I t, right, because phi of I t e, I t is a complex number which comes out, phi of e is 1, right, and phi x is alpha plus I beta, right. So, this is actually equal to phi x, right, that is the definition. Phi x is alpha plus I beta. So, this is just alpha plus I beta plus t. Okay. So, so far I have not done anything. So, now we have to bring in the C star identity, because we have to use that it is a C star algebra. So, look at Z star Z. Z star Z, what is Z? Z is this element x plus I t e, right. So, Z star Z, you multiply what is Z star? So, Z star is x star is x itself plus I t star, right. So, I t e star will give me minus I t e, right. So, this is like taking the complex conjugation, right, the star operation. So, if I multiply Z star and Z, I am multiplying x plus I t e and x minus I t e. So, if you do the multiplication, you will get it as x square plus t square e, right. Okay. So, you look at modulus phi z square, okay, Well, what is phi z? Phi z is alpha square plus. So, I should write this a bit more clearly, alpha square plus beta plus t whole square equal to, right, this is phi z. So, the modulus square of phi z is square of this plus square of the imaginary part, right, that is alpha square plus beta plus t square, that is mod phi z square, that is less than or equal to norm z square. Remember, if I have a multiplicative linear functional, its norm is less than or equal to 1, right. So, mod phi z is less than or equal to norm z, right. Now, I have norm z square. So, I can use the C star identity. So, that is z star z, right, norm of z star z, okay, which is less than or equal to. So, I have z star z to be here. If I take the norm of this, I have norm of x square plus t square, right, norm of E is 1. So, I will get less than or equal to norm x square plus t square. Okay. So, now I just look at what is there in the, okay. So, I look at these two quantities. Okay. So, alpha square plus beta square plus 2 beta t is less than or equal to sorry, plus t square also, right. So, plus t square, that is necessary, is less than to norm x square plus t square, right. So, the t square gets cancelled and I am getting alpha square plus beta square plus 2 beta t less than or equal to, so this is actually less than to norm x square, if you like, right, Banach algebra property. So, right hand side is independent of t, right, and I want this inequality to be true for all t, right. So, this is going to be true for every t in the real line, implies that constant beta is 0, right, that is where the t is, right, this has to be 0, otherwise it will not serve. But that is precisely what we want to prove, right, because we started with x hat at phi to be equal to alpha plus I beta and we proved beta is 0, that means x hat is real valued, right. So, this implies x hat is real valued, and that is same as saying A is symmetric. Okay. So, any C star algebra is symmetric. Okay. So, let us continue with examples. So, let us look at examples again. So, the first one is C of x, where x is compact T2. Now, here let us just complete whatever we were saying in the other classes. So, recall that the multiplicative linear functionals are, so okay, so maybe I should write sigma of the spectrum of the C star algebra C of x, right, that is identified with x, right. How was it identified? I take any point. So, if x naught is in x, I have a multiplicative linear functional, right. So, this is equal to f of x naught, right, and the maximal ideal corresponding to x naught is, you look at all those functions vanishing in C of x at that vanishing at particularly that point, right, that exactly at that point. Of course, it may vanish at other points also, but look at all functions vanishing at this fixed point x naught, that is a maximal ideal, right, and this is a 1-1 correspondence, right. So, phi x naught corresponds to m x naught, that is how we identified. So, the maximal ideal space got identified with x, right, any phi sub x naught is identified with x, and the Gelfand transform, what is the Gelfand transform? So, we saw this in the last class. Gelfand transform is the identity, right. So, I take f in C of x, I have f hat, that is the Gelfand transform. F hat is from sigma, the spectrum of the C star algebra, right, in this case to the complex numbers. So, f hat at phi x naught, right. So, every multiplicative linear functional is a phi sub x naught, and this by definition is phi x naught at f, which is equal to f of x naught, right. So, phi x naught and x naught once you identify, f hat and f is simply the same function, right. So, Gelfand transform is the identity map. Okay. Now, I want to say a little bit more. So, there are topologies on the spectrum and x itself, right. So, x is compact T2. So, capital X is compact T2. So, it comes with a topology, right, and sigma of C of x, which is identified with x, is sitting inside the unit ball in the dual, right, of the Banach algebra or C-star algebra. So, that comes with another topology. I want to say these two are same. Okay. So, that is easy. So, that way we completely identify the spectrum of C of x and x itself, right. So, note that. So, remember that this is all for compact Hausdorff spaces. Okay. So, note that if x alpha converges to x in capital X. So, capital X is compact T 2. So, it has a topology there, right. So, x alpha converging to x alpha is the net converging to x in that topology. Okay. Then, so this implies if I take any f in C x, so f is continuous. So, f of x alpha will converge to f of x for every f in C of x, right, for every continuous function x, implies, well, now we go to the multiplicative linear functionals and maximal ideals and so on. So, let us write it in that form. What is the meaning of f of x alpha converging to f of x? That is same as phi x alpha, phi sub x alpha. So, that is the corresponding multiplicative linear functional, f converges to phi sub x f, right, for every f in C of x, right. This convergence happens in complex numbers, right, which is same as saying phi sub x alpha converges to phi sub x in sigma of C x, right. Remember sigma of C x, that comes with this weak star topology, right, which is pointwise. So, phi sub x alpha converging to phi sub x means at each point f in the algebra this convergence happens. So, what did we get? Hence the map x alpha going to phi sub x alpha is, well, it is 1 1 onto we already know, and continuous map from x into onto sigma of C x, right. But then both spaces are compact, right. So, but x and C of x are compact and T 2, right, compact Hausdorff spaces, and I have a 1 1 onto continuous map from one space to the other. So, this map has to be a homeomorphism. So, implies x alpha going to phi sub x alpha is a homeomorphism. So, that identifies the space x and the maximal ideal space or the multiplicative linear functionals on C of x, right, completely. So, this map is a homeomorphism, and after this identification the Gelfand transform is simply identity. Okay. So, we will see that this that Gelfand transform is an extremely nice map, will happen for all C-star algebras. Okay. So, let us look at some other example now, which is not a C-star algebra. So, L 1 of z. Okay. So, remember this is a n in z, right, all two sided sequences which are summable, n in z is finite, right, and the norm is simply this one, right. So, that is a, now we know that this is a Banach algebra with the convolution product, right, with the convolution product. Okay. What was that? So, I take A and I look at B. So, A star B equal to C, where, so C is a sequence, the nth term in the sequence is given by A n minus k B k, right, k running from minus infinity to plus infinity, right, that is the, okay. Now, I want to find out what are the multiplicative linear functionals, okay. So, we will show that sigma of L 1 z. So, that is the spectrum of this Banach algebra L 1 z is can be identified with can be identified with the circle, the unit circle, okay, or e to the I theta, right. E to the I theta is theta run from 0 to 2 pi, okay. And the Gelfand transform can be identified with, so A hat. So, I take an A in L1 of Z. So, that is a sequence, remember A hat will be a function. So, the will be a function on sigma of the Banach algebra, right, on the maximal ideal space, but that is identified with the circle group, right. So, I should tell you what is A hat at e to the I theta is, and that should be a complex number. So, that is simply A n e to the I n theta and n z, right. For each fixed theta I get this number, right, that is my Gelfand transform. So, of course, we have to prove all this. It is also possible to define an involution. So, involution on L1 of Z. Okay. So, A star. So, I should tell you what A star is. A star is a sequence. So, its nth term is A minus n bar. Okay. So, this makes L1 of Z. This makes L1 of Z into a Banach star algebra. Okay. So, Banach star algebra, okay, but not a C star algebra, Okay. So, the C star algebra identity will not be true here, you can find counter examples. Okay. So, exercise. So, I will leave this as an exercise to prove that the C star identity is not true. Okay. Okay. So, let us find out the spectrum of L1 of Z. So, L1 of Z is a Banach algebra with identity, right. The sequence which is 1 at the 0th place and 0 everywhere else is the identity, and L1 of Z becomes a Banach star algebra with identity. So, we will show that it is actually a symmetric algebra, and we have already said that the spectrum can be identified with the unit circle. So, let us try to prove that. So, we will start with, to prove the above, we start with the following proposition. So, this is the general result, and we will apply it to this particular case, which is L1Z. Okay. So, let me write it here. So, let x naught be in A. So, A is a commutative Banach algebra with identity, right, that is always the case. At times it may be a star Banach star algebra also. Okay. So, I may not write it again, but it will be clear from the statement. Okay. So, let x naught be in A, then x naught hat, that is the Gelfand transform of x naught, right. Well, where does it, so it maps the spectrum of A, which is the collection of all maximal ideals or the multiplicative linear functionals on A, and we know that it maps into the spectrum of this element x naught, right. The range of the Gelfand transform is the spectrum, right. This is something we have already seen. So, this map is a, so what is the map? Let me write down the expression as well. So, how is it defined? X hat at phi equal to phi of x, right, that is how it is defined. So, this map is a homeomorphism. Okay. So, sigma A is sitting inside the unit ball of A star, right, and it has that weak star topology, it is a compact Hausdorff space. Sigma x naught is sitting inside the complex plane, it is a compact subset of the complex plane. This map is a homeomorphism. So, that will mean it is a 1 1 on 2 map, which is continuous, inverse will be automatically continuous because of compact T2ness, right. So, x naught hat is a homeomorphism, which means you can identify the spectrum of A with the spectrum of the element x naught, right, is a homeomorphism in each of the following cases. Each of the following cases. Okay. So, 1, A is generated by x naught and E, right. So, if you look at the commutative Banach algebra generated by x naught and E, if that is A, then we have a homeomorphism. So, the reason is that the multiplicative linear functionals will be completely identified by its action on x naught, because x naught generates everything, and the same goes for all the. So, all the statements are same. Okay. All the statements are of similar nature in the sense that you have a generating set, and so and generating set depends only on x naught, then you have this homeomorphism. Okay. So, x naught is invertible and A is generated by x naught and x naught inverse, right. If you have x naught and x naught inverse, then of course identity is there, and you look at the Banach algebra generated by these elements. Okay. 3, A is a Banach star algebra and A is symmetric. So, once you have the star operation, you can define symmetricity, right. A is symmetric and A is generated by x and x star, right. So, x naught star and the identity, of course. Okay. So, the third case is what is actually important for us. If you look at the Banach algebra or the sister algebra generated by these x naught star and so on, it will look like polynomials in x naught and x naught star, and you take the closure, right, with respect to the norm. So, if you get all of A, then it is essentially polynomials in x naught star and then the closure, right. That in that case also the spectrum of A. So, the spectrum of the algebra A can be identified with the spectrum of x naught. Okay. So, proof is sort of one line, because in all these three cases the multiplicative linear functional is completely determined by its action on x naught, right. So, that is the key word in all cases. Multiplicative. So, let me write, just use the notation so that it is easy. So, a phi in sigma A is determined by its action on x naught, right, or x naught star, right, or x naught inverse, x naught star and so on, which is all determined because if you know the action on x naught, right. So, I do not need to, I will rub off that part just so that there is no confusion. So, let us see why. So, in the first case A is generated by x naught, right. So, if phi 1 at x naught is equal to phi 2 at x naught, then phi 1 is equal to phi 2, right, because x naught generates the algebra. And so, for example, x naught square, phi 1 x naught square is phi 1 x naught whole square, and so it will be equal to phi 2 x naught square and so on, right. So, phi 1 and phi 2 will be equal on the algebra A itself. Okay. So, x naught hat, is a 1 map, is 1 1. I know that it is continuous and it is onto, right, because it gives me everything in the spectrum of x naught. And so, I have a 1 1 onto continuous map from a compact Hausdorff space to another compact Hausdorff space onto another compact Hausdorff space. So, it is a homeomorphism. Okay. And the same works for both the other two cases to phi x naught. So, it is invertible. So, phi x naught inverse will have to be equal to phi x naught inverse, and so again the and the above argument works. right, because x naught and x naught inverse generate everything. So, if I have phi 1 and phi 2 agreeing on x naught, it will agree everywhere. So, you get a 1 1 map. Third one because of symmetry and so on, symmetric algebra, right. So, phi x naught star is going to be equal to phi x naught bar, right. Star goes to complex conjugation on the other side, that is your symmetric algebra. So, again as above the argument works. Right, because x naught and x naught star along with identity will generate your algebra, and so if phi 1 and phi 2 agree on x naught, then phi 1 and phi 2 will agree on x naught star, and phi 1 and phi 2 agree on E anyway. So, it will agree on the algebra generated by these 3 elements, which is the whole A, and so we are done. Okay. So, what we have proved is whenever the algebra is, so this is something you can keep in mind, that whenever the algebra is generated by a single element, the spectrum of the algebra and spectrum of the element are same. One of the reasons you call spectrum of A, the word spectrum comes from this, right. So, once they are identified, you have so you are identifying the spectrum of A, which is the collection of maximal ideals or multiplicative linear functional to be a subset of the complex plane via the spectrum of this generating element x naught. Okay. So, we will stop here, we will use this to study the spectrum of L1 of z, right, that is our aim. Okay. So, let us stop here.